Hello, in this video we'll focus on basic signals, convolution, deconvolution, and the topic of LTI systems and their interconnections. We'll first start by introducing the stem plot in Matlab. Next we'll talk about the unit step function as one of the common signals. After that we'll talk about the unit pulse or the delta function. After that, we'll move on to convolution, deconvolution, LTI system diagrams, and finally, Matlab structures. Similar to the plot function in Matlab, we can call the stem function, which is another built-in function in Matlab, to help us plot discrete signals in form of stems, hence the name stem. The way you call the stem function is the exact same way you use the plot function, except the graph you will get at the end is different because it's used on discrete signals. So the code that is given here will produce this graph in Matlab. We have the absolute function, but in discrete form. So n is a discrete variable ranging from -5 to 5 with an increment of 1, and y is the absolute of n. We called figure to open a new figure window. Next, we called stem this way. Just like how we used plot, we have to put the independent variable first, in our case it's n, followed by the dependent variable, which is y of n. Y is a function of n, that's why we put it after n. The rest is very similar to the plot function. We have to use x label, y label, and add a title using the title function. The unit step function is defined as u of n is equal to 1, where n is greater than or equal to 0. So wherever n, which is the value of the x-axis, is greater than or equal to 0, the output y is equal to 1, constant 1. Where n is less than 0, which is the negative half of the x-axis, y will be equal to 0. In Matlab, we can define the unit step function as y is equal to n greater than or equal to 0. So this means we will check for each value of n compared to 0. While n is greater than or equal to 0, then y will be 1, or logical 1 in this case, otherwise it will be 0. The name of the function here is unit step, the input is n, the output we named it y. And notice that n here, for the one that is plotted, is simply just n. And we can have different inputs for the unit step function, such as u of n minus 1. In this case, the signal will be shifted to the right one step. On the other hand, the delta function, or the impulse function, is defined as delta n is equal to 1 at n is equal to 0. So when n is equal to 0, the output of the delta function is 1. Otherwise, it is equal to 0. In Matlab, we can implement the delta function using the following code. The name of the function is delta, the input is n, and y, which is our output, is defined as n equals 0. That means we're checking each value in the array n. Where n is equal to 0, y will be equal to 1. Otherwise, y will be equal to 0. Now our next topic is convolution. Here we see the formula for convolution. In another video, we'll be explaining the formula, but simply put, you can define convolution as an operation between two signals, and the output of this operation represents how a signal can be modified by another signal. We can implement convolution or understand it through an example. Here we have a signal named x and a signal named h. The way it works is that we keep x as it is and we flip h by obtaining h of minus k. Once we flip h, we will shift it along x, and then at each shift we will find the intersection points between x and h after we flipped it, and these intersection points we're going to multiply their values, and that will give us the value of the convolution at that particular point. So convolution in Matlab can be obtained using the conv function, which simply takes two inputs, which are the signals that you want to convolve together, and it will give you the output of the convolution. So this is an example of convolving two signals, f and g, and then plotting the output using the stem function, which is used to plot discrete signals. So our x-axis here is actually n, and n starts at 0 until it reaches the maximum value for n in the array y, which is defined as length of y minus 1. So from 0, increment by 1 until you reach length of y minus 1. This is going to be the x-axis, or the values for n, because we're plotting y of n. For the y-axis, we're gonna put y, which is simply our signal that we want to plot, which is the convolution of f and g. Deconvolution in Matlab is obtained using the deconv function. As an example here, we have y is equal to the convolution between f and g. To obtain f again from y, we can deconvolve g from y. So that will give us f. That means y is equal to f convolved with g. To get f, or to extract f from y, we can use deconvolution between y and g. Now we'll move on to the topic of linear time invariant systems and how we can obtain or calculate the impulse response of such a system. The impulse response of a system is defined as the output of that system if we apply the impulse function or the delta function as its input. So as an example, we'll solve the output or the impulse response of this given diagram. We have 4 signals connected such that some signals have the addition operation between them, and usually these signals will look like they're connected in parallel. These signals, we have to perform addition between them, and other signals are connected in cascade mode, such as x with h, or f with w, or the entire, or the 3 signals x, f, and w. These signals, we have to perform convolution between them. So let's solve the impulse response for this diagram. We'll express y mathematically as y is equal to f convolved. You can use double asterisks or just one. F convolved with w and then we have to add h to this result, so we say plus h. Okay, now we took care of the right half of the diagram. Now the rest is, or the remaining signal is just x by itself, and x is convolved with the right half of the diagram. So I have to put a bracket just to emphasize that I have to perform this addition first before this convolution. X convolved with f convolved with w plus h. Let's put it clearly once again. We'll say the impulse response y is equal to x convolved with f convolved with w plus h. I don't need to put the bracket here because convolution has higher priority. So the bracket here is optional. Just to make it more readable, I'm going to add it around f convolved with w. Now, translating this into MATLAB code might require multiple steps. In brief, we will call conv to convolve f with w, like that. And we can store this in a temporary variable. I will call it t1 is equal to semicolon. The next step is to add t1 to h. So we'll say t1 plus h. However, the size of t1 will be different from the size of h. t1 will most likely be larger than h. So before being able to perform addition between t1 and h, I'll have to make sure that the size of h is equal to the size of t1. So we can say h bracket length of t1 is equal to 0. This will ensure that the size of h becomes equal to the size of t1. I'm assuming that the signals x, h, f, and w have the same size. This way, when I convolve f with w, I'll get a bigger or a longer signal. So now, adding t1 to h is possible. And I will store this in t2. So I will say t2 is equal to t1 plus h. Finally, I'm able to calculate y in MATLAB code as the convolution between t2 and x. Here I don't have to worry about the size disagreement because convolution does not require that the input signals have the same size. So I do not need to worry about padding any of t2 or x with zeros. But I'm going to put a semicolon here because this is just an intermediate calculation. If I'm interested in reading y or the output, I can remove the semicolon. And I can also plot it by saying stem, assuming it's a discrete signal. From the brackets here, the square brackets, I can tell it's a discrete signal. So stem will start with 0 until we reach the length of y minus 1. That's for the x-axis. The y-axis will be simply y, semicolon, which is optional. And of course, x label is x. Y label is, it's all lowercase by the way. Y label is, I will call it y. And maybe the title can be the impulse response. Now we'll do another example on finding the impulse response of a given LTI system diagram. We have f, g, h, and x as signals within the diagram, and we can tell clearly that f, g, h have convolution between them. So we have to perform convolution between f, g, and h, and the output of this convolution must be added to x. So we can write this or express it mathematically as y is equal to f convolved with g convolved with h plus x. To translate this to MATLAB code, this is not MATLAB code yet, so to translate it into MATLAB code you have to call the convolution function, but the convolution function only takes a maximum of 2 inputs, so we have to split the convolution between f, g, and h into 2 steps. I will do it all in one line of code. I will call this variable instead T1 or temporary 1, the first temporary variable. It will have in it the convolution of f with the output of the convolution between g and h. So the convolution between g and h will be calculated first, and that will be convolved with f to give me f convolved with g convolved with h. You can add that as a comment saying this is actually f convolved with g convolved with h. Now all I have to do to obtain y is to add t1 to x. So I will say y is equal to t1 plus x. However, since the size of x is, or if the size of x is smaller than the size of t1, then I won't be able to perform this addition. Matlab will give me an error. Therefore, what I'm going to do is expand x by assigning it zeros at the end. So I will say x, open a bracket, length of t1 is equal to 0. So what this will do is add zeros towards the end of x such that it is going to be equal in length as t1. Now addition is possible between t1 and x, and that will give me the final impulse response. Similarly, if I want to plot this, I will simply call stem. The x-axis will be 0 until length of y minus 1. The y-axis will be y, which is what we saw in the previous slide. The last topic in this video is structures in Matlab. A structure in Matlab allows you to create variables with different fields. So as an example here we have a variable named rectangle, and we know that the rectangle has two features or two fields, the height and the width of the rectangle. So instead of creating two separate variables, I simply created one variable. I named it rectangle, and I mentioned that this variable has two fields in it, the height and the width. And I specified that the height is equal to 3 and the width field of the rectangle is equal to 4. So when I call rectangle to look at what it looks like, Matlab outputted for me the fact that the rectangle is a struct and it has these fields. The height is equal to 3 and the width is equal to 4. And I can normally, or I can perform operations on the fields of a struct in Matlab normally by simply extracting these fields by putting a dot followed by the name of that field. So I'm calculating the area of that rectangle as the width of the rectangle by calling rectangle.width times the height of the rectangle by calling rectangle.height. So Matlab created a new variable named area and stored in it 3 times 4, which is 12. So this is how to use struct in Matlab, or the structure in Matlab. We will use Matlab structures to help us calculate the convolution between two signals that have different starting values. So as an example here, I'm creating a variable named f, or a signal named f. The signal has the values 1, 2, 3, 4 in it, but it starts at 3. So f, that the starting point, sp, is equal to 3. Similarly, I'm creating a variable named g to store signal g in it. Signal g has the values 1, 2, 3, and it starts at 2. So g, that starting point, is equal to 2. So each signal here has two fields, the data part of the signal and the starting point of the signal. So when I try to calculate the convolution between these signals, I will create a new variable. I will name it y, for example, and y will have two fields as well. The data part will be equal to the convolution of the data parts of f and G. So I'm convolving f.data, which is this array, with g.data, which is this array. Now all I have to do is define the starting point of this signal, which is the convolution. The starting point field of y is equal to simply the summation of the starting point of f with the starting point of g, which is going to be, in our case, 3 plus 2, which is simply 5. This is a summary of the user-defined functions that we'll need to use in this lab, which are simply the unit step function and the delta function. You can leave them at the end of the file, so you can use them as needed within your script file. This is all there is in this video. If you have a question, please let me know.